All right. I am excited to welcome the gentleman from the Advanced Refrigeration podcast, the mans, the myths, the legends, Brett Wetzel and Kevin Compass. Thanks for joining me, guys.
How we doing tonight, Brian?
Thanks for having us on, Brian.
So today we're going to be talking about identifying parts of a supermarket system. But before I do that, because both of you guys are new to the podcast, I just want to go through and have you kind of introduce yourselves, talk a little bit about your experience, and then also talk about just why you started the podcast, and then at the end we'll kind of tell people a little bit more about how they can find your podcast and everything you guys do. But I'll start with you, Kevin, since you're going to have to muddle through with your horrible internet connection.
All right, guys. I'm Kevin Compass. I am a supermarket refrigeration startup technician. I've done just about everything from air conditioning to commercial air conditioning to refrigeration to supermarkets. And now I spend the majority of my time designing controls and installing controls and starting up grocery stores all around the country. I basically, travel all around the country, commissioning and starting up grocery stores and doing energy management projects and energy saving optimization of grocery stores. So I've been around just about everything from chillers to supermarket refrigeration racks. And we have this podcast that we also do that brings in the refrigeration side of it. So we're trying to grow the refrigeration side of the podcast world. And it's basically my story.
Awesome. Yeah. Anything that gets more people educated or interested in the corrosion refrigeration space is a good thing. I'm all for that. So how about you, Brett?
So my name is Brett Wetzel. I'm the manager of technical troubleshooting and training over at Coalescing. I've been doing refrigeration, if you include my electronics background, about 18 years. Worked on anything from a small little self-contained up to 1,000 horsepower ammonia screw. So I've done a gambit of different stuff. I worked on a whole bunch of EMS, different programming, different systems. And, like Kevin said, we started this podcast because we just wanted to help educate people, and it seems to be doing its job.
Yeah, absolutely. It's filling a really important gap that we had in the sort of media space. And honestly, even when we got into market refrigeration, which would have been, 6 years ago, whatever it was, we really came from the air conditioning side. And a lot of this stuff, I wish your podcast was around because it would have made it a lot easier. We muddled through and figured a lot of it out, and still to this day are, learning a lot more about it. But it's really nice to have some of this content out there. And you guys really are. I mean, it's advanced refrigeration because a lot of it is pretty advanced. I mean, a lot of it is pretty in depth. But today, we're going to be starting with the basics because we recognize that there's a lot of technicians out there who are primarily air conditioning technicians. A lot of them are even residential, but who have an interest in maybe getting into some of these different segments. And honestly, my take on market refrigeration work or grocery refrigeration work is it's some of the most interesting, complicated, yes, but really just elegant and interesting types of systems out there in the industry. So we're going to kind of go step by step through each component, and I'm just going to let you guys riff on it. I mean, I'll ask questions if I've got them. I'll ask the stupid questions so you can deride me, laugh at me, point fingers, ha ha ha, Brian's an idiot. So, but other than that, I'll let you rock on with it. So let's start with compressors, and I'll let you guys take it from there wherever you want to go with it.
In a supermarket, in a parallel rack application. So instead of like a normal refrigeration or air conditioning system, you having one compressor and one metering device and one evaporator and one condenser, now we have this gigantic, massive multiplex system. When I say multiplex, I mean there is multiple compressors, multiple evaporators, sometimes multiple condensers, multiple metering devices across this whole supermarket. So instead of having, back in the day in the early 60s and 70s and 80s, they would have single systems. They would have, the meat cases would have their own compressor, condenser, and metering devices, and it would be separate. Now, as things advanced, we started putting systems together. They become more efficient, more reliable, more redundant, because everything about refrigeration is about redundancy. We're trying to keep food cold. We're no longer trying to keep people comfortable. Now we're trying to keep product cold and preserve product. Everything about this is about preserving product so people could sell product. Instead of having one compressor for the system, now we have multiple compressors on this refrigeration rack. So you start out, you have multiple compressors of different sizes. Some of them are the same size. Some of them have variable capacity, meaning VFDs. Some of them have unloaders on them. Some of them have digital compressors. There's all kinds of ways: screw compressors, recip compressors, scroll compressors. It could be any of these, the way it's set up. And they are piped with a common suction or discharge manifold. You have a common suction manifold, and you have a common discharge manifold. So all the compressors are piped together. So you are able to meet the demand of the system, the saturated suction temperature. You're able to meet that demand by cycling on and off compressors or varying the speed of compressors. So we are able to, instead of cycling a unit on and off on temperature, now we are able to take that and we are able to manipulate the saturated suction temperature of the system to meet the demands and load of the supermarket. So now we are able to tailor this system to the demands of what we need. So we have just the standard compressors. We have a suction header that your suction return gas is coming to, and then we come to a discharge. We come out of the compressors, we go to a discharge header where all your compressors tie into in a row. They all tie into a discharge header. Okay. And after they all discharge together, so now we have to deal with oil. Oil is probably one of the hardest things for guys to deal with in a supermarket, and probably the most problematic thing of the supermarket rack refrigeration system. So we have to capture this oil because we have to feed all these compressors back this oil. Because we have oil coming back from the system, we need to get the oil back in the compressors. So after it goes through this common discharge manifold, and it's going to go into an oil separator. This oil separator is going to capture the oil and return it back to the compressors. Now, in a supermarket rack refrigeration system, you could have several types of oil separators. You could have a coalescent oil separator, which would be a filtered element that is going to cause the oil to aerate from the refrigerant and drop down. It filters the refrigerant and it causes the oil to separate by aerating it. And the oil's heavier, so it drops down into the oil separator. Now, you could have a you could have a centrifugal type of oil separator, which is a screw type. So it is basically a screw inside of a cylinder. The discharge gas and oil get forced up the screw. The oil comes back down the screw because it's heavier and it falls down to a reservoir in the separator. Or you could have what they call an impingement type separator. An impingement type separator is a common what you see in old systems. It is basically a cylinder. The oil or the discharge gas and oil come through, hit a screen, and in that screen, it causes it to aerate, kind of like the coalescent, and it causes it to drop out and fall down. Now, all three of these separators have different benefits. They're all the centrifugal is better than the impingement type. The impingement type is probably the least efficient. The coalescent is the most efficient. It's going to separate the most oil, and it is going to clean up the refrigeration system as more than the other two would. Right, you want to take the rest of the oil system?
Sure. On this part of the slide, we have, like Kevin just went over, the oil separator, which then is going to feed into the reservoir. This happens to be a low pressure type system. you basically have two different pressure drops. So you have flow, because we can't have flow without, having different pressures, right? So, going from the oil separator, let's just say our discharge pressure is 200 pounds. You typically on the top of the reservoir, we have what's called an oil differential valve, and that's what's actually going to give us the reservoir pressure. Typically, this is either an OCV 5 or 10 or 20 or 30, and what that's doing is basically wherever the OCV is actually piped into, that's giving you a pressure above whatever suction pressure it's tied into. On this particular system, the OCV is tied into what looks like the medium temp type of the system. So what that's going to do is, let's just say the medium temp side is running at 40 PSI and we have an OCV 30. That means inside that reservoir, we're going to have approximately 70 PSI of oil pressure, which then is going to, get filtered through the oil filter and then get delivered to all the rest of the compressors through the oil level controls, or sometimes they're referred to as oil pots. If you notice, the OCV is tied into the medium temp side of the header. The reason for that is because we don't want the oil line off of the OCV hooked up to the lowest suction, because if we were to do that, we wouldn't have enough oil pressure to actually go into the suction header, to go into the crankcase of the compressor.
Got it. Because you're, just to clarify the reason that is, and because I think, again, a lot of air conditioning guys aren't going to catch this quickly. It took me a while to get this, is this idea that your pressure that you have in your suction header is going to be the lowest pressure that exists within the system. And obviously your medium temp suction header is going to be a higher pressure than any low temp. And that's obvious because we're talking about suction saturation temperatures. When you have colder temperatures, you have freezers, you're doing ice cream, you're doing frozen foods, that's going to be a significantly lower suction saturation. And in this case, if we were to have tied it into here, then our pressure wouldn't be high enough to push into the crankcases of our medium temp compressors. Whereas if you're using medium temp suction, that will still be high enough, obviously, to push into the low temp.
Correct.
Got it.
Yeah, because otherwise, usually 99% of the time, it's always going to the highest pressure header. Sometimes you'll see it if you have two medium temp racks. Sometimes you'll see it piped into, the lower of the two. That's not the correct thing to do. But the way it should be piped in is just like it's shown. It should be going into the highest pressure header to make sure that we have that correct differential pressure, to make sure we can get that oil supplied into the oil level controls to fill those compressors up so they don't dry out.
I'm going to kind of step in and just play the stupid air conditioning guy here every once in a while, just so that way we don't get too far ahead of where everyone is. And I just want to state the obvious, which is that when we're talking about oil, it's so critical in these systems because you have all of these compressors that are sharing oil. And so obviously you've got to have oil that's continuously returning to all these compressors. And it's so critical that that oil doesn't end up out in the system, kind of getting lost out in these giant systems. Because you have these, miles of pipe work, probably exaggeration, but a lot of pipe work going out into the store. You have all these evaporators. And if you've got oil that's making it out, and a little bit will, but very little amount. But if significant amounts of oil is making it out into the store and not making it back, then you're going to have, pretty severe issues. And you're also going to have performance problems because that oil is not good. We don't want it out in the store. We want it just returning back to the compressors. And that becomes so critical in market refrigeration. It's like the magic sauce in market refrigeration that when somebody who's used to air conditioning shows up, it's like, what is all this stuff? And it's all about making sure that you get proper compressor lubrication.
After you leave the oil separator, guys, we get to a check valve. So we're going to have a discharge check valve. So this discharge check valve does a couple things. It prevents refrigerant migrating back into the oil separator if the system were to shut off. So say the compressors were to shut off for a safety reason, or the compressors were to some kind of safety situation, they shut off, or if the system was to satisfy in the middle of wintertime via low load issue, you don't want all that liquid migrating back into the oil separator, because once it migrates back into the oil separator doesn't know if it's liquid refrigerant or oil. All it knows is that it's going to allow it to flow into the reservoir, then flow straight to the compressors. So obviously you don't want that. So that is going to cause liquid to enter your compressor. So that check valve is there to prevent that migration of liquid refrigerant during a safety situation and a low load situation.
So in other words, liquid oil in compressor crankcase, good. Liquid refrigerant in compressor crankcase, bad.
Yes, very, very, very bad. So after we leave that check valve, now we're going to come to it. This isn't on every rack. This is just depends on the customer application. You could come to a three-way valve. You could come to some automated ball valves if you have heat reclaim. So heat reclaim is basically we're taking the discharge gas out of this machine, this rack, and we're using it to heat something, whether it be the snow melt system for the store. Like we have in Chicago, we have a lot of snow melt stuff. So we're melting the snow on the sidewalks or in the gutters, whether we're using it to warm up a water heater. So we have a refrigerant heated water heater. So we're picking up it's using the refrigeration heat to heat up the hot water for the store, or it could be using it for air heat, meaning we're heating a coil on a rooftop or an air handler or a unit heater in the back room where we're using the refrigerant heat to reject in the system. So now this becomes even more efficient because now the system's removing heat from the cases, it's refrigerating the cases, and it's taking that heat and it's using it to heat the store.
Yeah, we see this a lot in Florida for all the reasons that you mentioned, other than all the snow stuff, because we don't know what that is. But we use it a lot for reheat for dehumidification as well. So, you know, when you have a need to dehumidify, but you don't have a need for comfort cooling, then you can, you know, cool the air, drop the moisture, and then reheat it using that excess heat that you had from the rack refrigeration system.
Yeah, I wish we had more reheat around here. We're not allowed to have that.
Yeah, any places that a lot of times that have high humidity. When I was up in Connecticut, reheat was just, it had to be there because otherwise, you know, the store would get super cold, but then be just miserable humid because you know basically it would reach maybe 66 degrees in there because it would pull down so quick. But yet, you know, it needed that reheat to stay running to make sure you keep the store a little bit warm to keep a load on the compressor so they didn't actually maintain temperature.
Yeah, it's actually fairly rare in Chicago now. They make it very difficult for us to have reheat with all their safety stuff. We're using that. We're using that either three-way valve or automated ball valves or solenoid valves to reheat that. So the way this works is this three-way valve, it rejects, it sends refrigerant one way or the other. So when it's energized, it allows a plunger to move inside of it and shift the way the refrigerant goes. When it's de-energized, it's going straight to the condenser. It's going straight out towards the condenser. When it's energized and it's in reclaim mode, it's sending all the refrigerant through that reclaim tank or coil or whatever it is. And then it's going back through a check valve so it can't flow backwards, and it is directing that towards the condenser. That may not be on every rack. It just really depends on the application of what it is and how the customer designs it. So after it leaves the reclaim, if it's there, then it's going to go to our condenser splitting valves or three-way valve. So again, we have another three-way valve, or we have solenoids. We have to control our condensing pressure. With this rack, I mean, you could be running, it could be sized for 115 degrees, and it could be needing to run at a minus 20 degrees. This machine runs all year round. So we need to be able to tailor this machine to our conditions. Say in Chicago, it goes from 100 degrees all the way down to, you know, last year it was minus 20 for a couple days. So if we were to use, say we have this massive 12 fan condenser on the roof, if we were to try to use that condenser when it's that cold, we would never have enough refrigerant in the system to operate that condenser. It would be so massively oversized, we would never need it. So what we do is we split the condenser in half. We do this with splitting controls so that we have a three-way valve in this picture. So in this example, so this three-way valve, when it's de-energized, it allows refrigerant to go to both sides of the condenser. The plunger is down. Or I'm sorry, it's up, and it's allowing everything to go. And when it's energized, it's in split mode. It only allows refrigerant to go to one side of the condenser. So in the wintertime, so usually 40, 50 degrees, most grocery stores, they shut off one side of the condenser. So now we're able to better match the condenser operation to our actual ambient temperature. So instead of having a massively oversized condenser, now we have a more appropriately sized condenser for the ambient temperature. Now, like I said, you can have a three-way valve. Some customers use solenoids, and they're always going to be normally open. They should be, because you always want refrigeration to fail on. We would use normally open solenoids, three-way valve, electronic stepper valves to do this, electronic stepping three-way valves. There's all kinds, and actuated ball valves. There's multiple different ways to do this, but that is how we take the condenser and we split it in half for wintertime.
If you notice in this pictorial, you'll see that there's two check valves on the outlet of both sides. Now, what he was stating before about, having normally open solenoid valves on the inlet side, the reason why we have both those check valves there is because when it does go in a split, we need to remove that refrigerant from there. Otherwise, it'll just log in there during the wintertime. And that's why we have the solenoid on the blue line coming off the bottom check valve. Basically what that's going to do is when that three-way valve shifts, it's going to stop the flow on the, summer side of the condenser that's labeled there. The check valve is going to prevent refrigerant flow from coming back up the actual drain leg or drop leg is what we refer to it. And then basically that normally closed solenoid line that's on the blue line there heading to the suction line, which is on the green, is going to open up to remove that refrigerant. In the same hit, it's also going to pump out the refrigerant on that other line on the three-way valve in this instance and head out towards the suction line to remove that refrigerant. And basically that'll end up in the receiver.
Yeah, because you don't want a bunch of refrigerant just sitting there.
Absolutely.
Makes sense.
And then we have, from here, we have the A8 pressure regulating valve. That is a inlet pressure regulating valve. So what all that cares about is the pressure on the inlet side towards the condenser. Basically there, if you have in the middle of winter time, you might have the temperatures where it's going down to 0 or even 30, like here in Texas, we'll start having head pressure issues. And basically you set that valve to a certain PSI to maintain that certain head pressure, just like you were on smaller commercial stuff where you have a headmaster where it's labeled 180 pounds or 150 pounds, which I know a lot of you guys have already seen out. But because these lines are so big, we need to be able to use two separate valves. If we tried to use a headmaster on a rack refrigeration, it'd probably be 2 foot big. So instead of that, we use the A8 valve for the inlet pressure regulator and the A9 as an outlet pressure regulator as the hot gas bypass. Basically, we refer to it as a receiver pressurization valve. So if the A8 valve starts holding pressure back, that means the outlet of that valve is going to start going down in pressure. Well, we don't want that going too far down because our expansion valves need a certain pressure in order to operate properly. That's when the A9 will start pressurizing hot gas into the receiver to help push that refrigerant out. To push it out to our expansion valves or wherever it might be going.
Yep, makes perfect sense. A lot of very specific purposes for each one of these valves, and though they may look similar, they have very different purposes. And I think that's why being able to identify all this is so important, because it can get confusing fast.
So from the drain leg or drop leg is what we referred to it earlier. That refrigerant is then going to head into the receiver. Typically we try to maintain anywhere from 15 to 30%, depending on what the manufacturer wants, what the customer wants. And this is just to make sure that we get a liquid seal going out of the receiver to ensure that we have a full column of liquid leaving the receiver, which goes to the liquid line. This is very, very specific. When you're talking with someone trying to diagnose something, there is a major difference between drain leg or drop leg and liquid line. So just make sure that you understand you're only ensured that you're going to have a full column of liquid coming out of that receiver due to the way that the receiver is actually piped internally.
Yeah, you're going to have a very low subcooling number. Like a lot of guys are used to seeing, subcooling with an air conditioner. You're going to have a very low subcooling number coming out of that receiver, maybe like 2 to 3 degrees if you're lucky on a great day. It's going to be extremely low. That liquid receiver is ensuring it has a dip tube in it, and it's picking up liquid in there, and it's ensuring that we have a full column of liquid going out to our expansion valves. because we can't maintain a subcooling number because our condenser is not backing up refrigerant in there. We have a system where we're having a receiver because our charge varies so much because things are shutting off, things are turning on, things are going through defrost, things are affecting the system load-wise. So that's why it's not a critically charged system. Uses a receiver to hold the excess charge, like a buffer tank almost.
You've got extra. You've got extra because you have a lot of different things that can go on in the system where you need a variable amount of refrigerant. And I also want to mention, because that was actually something that blew my mind, the whole drop or drain leg. It's like, that's the liquid line, right? It's coming out of the condensers. We always say the line coming out of the condensers, that's the liquid line. Well, no, because it isn't necessarily going to be even full of liquid. You know, that's not how it's designed. The one that's going to have the full column of liquid is the one coming out of the receiver. And also there's just, if you confuse the two, then when you're talking to somebody on the phone, they're not going to have any idea what you're talking about.
So specifically in industrial systems, it's funny because sometimes there is sight glasses on the drain leg, and they basically, you'll see the refrigerant trickle down going into the receiver, and vapor is actually going back up to get recondensed because obviously the liquid's heavier than the vapor. I'll take the super hard one. So coming out of the receiver, we go down to the filter dryers. This is to ensure any type of debris going through the system is getting caught before it goes into the, any of the expansion devices or, anything critical that could, basically gum up, which then in turn then goes to the sight glass. This is just to, really just to ensure that you do have a full column of liquid going out from your filter dryers. A lot of times you could have a receiver level of 30, 40, 50%. And if you have some sort of blockage in your filter dryers, you will actually see flashing in that sight glass.
Unlike a normal system, our air conditioning system, we want it with a receiver. We want to see a full sight glass all the time. So we want that sight glass to be full all the time. If it's not full, then we have an issue, whether it be like a low receiver level, plugged filters, plug screen, that sight glass needs to be full all the time in order for us to have proper flow to our valves. Now, after we leave the dryer and a liquid line sight glass, depending on the system, you're going to see this more on low temp systems, and a lot of newer stuff, both low and medium temp, meaning freezers and coolers, are starting to use subcoolers. So what we're doing on this, so since we can't gain subcooling by backing gas up in a condenser on a traditional rack because we have that receiver there, so now we have poor subcooling going out there. We have a solid column of liquid, but we have 2 to 3 degrees of subcooling, maybe 5 if you're lucky, going out to those valves. Well, that doesn't lead to the best valve performance, especially when it's 100 degrees outside and that liquid's 100 degrees. Your 100-degree liquid is not very efficient feeding those valves. So everything's about efficiency here. So especially when you get to low temp, when you start seeing this, you start seeing low temperature refrigerant. It takes a lot of horsepower to do that. So in order to make this system more efficient, we are mechanically subcooling the liquid. So what we do is we take a brazed plate heat exchanger and we are running the liquid line through it. And then on the other side of it, we have a refrigeration circuit. This could be done a couple ways. This could be, say you have a low temp rack and you're using the medium temp rack to subcool it. So we're using the medium temp rack to cool the liquid of the low temp rack. This allows us to bring our liquid temperature down to 40, 50 degrees, whatever the customer design is. And this allows us to do a couple things. It allows us to run smaller liquid lines because now we don't have to worry about the pressure drop as much. It allows us to have smaller expansion valves because now we're able to feed that with more efficient liquid. And it allows the system to be more efficient because now you're feeding that expansion valve with, say, 50 degrees of subcooling, and now you don't have as much flash gas going into that valve, and that valve is going to be way more efficient. So it makes the system more efficient. You could actually have smaller compressors. The whole rack could be smaller because you're running that efficient 50, 40 degree liquid. Now there are racks that self-subcool. When I say that, they're economized. They have economizers like some screws do. With economizers, basically the compressor has an inner stage, meaning a second stage of it, that is actually running the subcooler. So the subcooler is no longer a parasitic load. It's a cancelization out. So you don't lose any BTUs by subcooling it, and you gain BTUs. So it's a win-win on both sides. Whereas if I was using the medium temp rack to do this, I increase the load on the medium temp rack now instead of just keeping it all in the same rack. So that's the two different ways that they're doing it. So mechanical subcooling allows us to make the system all around more efficient.
Yeah, and in simple terms, because we say brazed plate heat exchanger, and some guys are like, well, I don't know what that is. Like, this is an evaporator. That's what it is. It's a direct expansion evaporator, and you're using another evaporator in order to cool the liquid. On this particular rack, in this case, we're showing it using another medium temp rack. So it's really simple, the design. It makes perfect sense. But like you mentioned, it does add load because it is another evaporator coil that's on that other circuit.
Also, one more thing that I wanted to mention, you'll see that any kind of brazed plate heat exchanger, as you referred to as the evaporator, basically always has it's doing counterflow. So if you look on this actual pictorial, you'll see that the expansion valve is there at the bottom and you're feeding the warm liquid at the top. That's to get the most efficiency out of that brazed plate heat exchanger as humanly possible.
Yeah, and that's the same even if you're doing anytime you're using a heat exchanger, you're almost always countering flows, whether it's water on one side and refrigerant on the other, some sort of secondary fluid like CO2, regardless, you're almost always doing counterflow to get maximum heat exchange.
Yeah, the only reason why I bring it up, because I know that, sometimes when these things are put in aftermarket where, they're doing a retrofit, sometimes they're piped in incorrectly and they're wondering why I can't get it down in temperature. Well, that's the reason why it's not piped in counterflow. This is the OLDR, the liquid differential regulating valve. This is placed on the liquid line coming out of the liquid header. The purpose of it is to maintain a differential during defrost. So that top evaporator, if you notice underneath the expansion valve and underneath the liquid line solenoid, there are check valves in the opposite direction of where the refrigerant typically flows. During defrost, what will happen is off of the discharge header, there is a two-way solenoid valve right connected from the red line going into the green line. What that's doing is putting hot gas into that evaporator. Now, what would happen is if that OLDR did not exist, basically that evaporator would end up just filling up with whatever pressure that the discharge pressure was currently running at. We would have no flow. It's not really the hot gas that defrosts that coil, it's the latent heat exchange. So basically, we need to have flow running through that evaporator in order to achieve defrost. So what will happen is when that valve, the OLDR, goes into differential mode, it's actually creating a differential of anywhere from 20 to upwards of 30-pound differential. What that's doing is actually making the discharge pressure 30 pounds or 25 pounds heavier than what the liquid pressure is. This is to ensure that we can actually flow vapor through that two-way solenoid valve into the evaporator, bypassing the expansion valve, bypassing the liquid line solenoid and going back into the actual liquid header. Because when we're doing this, we're actually creating liquid. We're taking that hot gas, we're actually de-superheating it, making a latent heat exchange, which is really what's doing, most of the defrosting, and then in turn going back up to the liquid header itself.
Yeah, that evaporator is becoming a condenser, right? It's actually using, taking the ice that's on that evaporator coil and the lack of heat that's in that evaporator coil, and it's condensing that hot gas that's coming from the defrost header, and that's really what's doing the work. Like you said, it's a latent heat exchange, and that's once you kind of get your head around that, it's a eureka moment. OLDRs, I kept talking to Nathan about it when we first started. I'm like, what? I don't understand what's happening here. And then finally, it's like, oh, okay, now it makes sense. In order for it to get back into the liquid header, there has to be a pressure differential between this defrost header and the liquid header, and the OLDR is what allows that to happen.
Yeah,
it's very similar to a heat pump with a few added components.
See, now you're speaking my language.
It's very similar to a heat pump. See, we break apart our three-way valve, and it's broken apart. So It's a couple different components, and then the OLDR is a added component. Now you could replace that with a DDR, which would be a defrost differential. So instead of doing liquid defrost or latent defrost, we could do hot gas defrost, meaning we're taking discharge gas just like a heat pump would. We're taking discharge gas and shooting it back down the suction line, and we're defrosting the coil that way with discharge gas. Discharge gas has more benefits to it. I mean, it's a faster defrost. It's a more efficient defrost. It's all around better in humid climates to use that. But I mean, it does drive up the head pressure. So that is the non-benefit to it.
All right, who's going to take the ever complicated ball valves?
Oh, this is a difficult one. I'll do it. So I just labeled this one ball valves because it doesn't, basically it's going to dictate wherever, the name of the valve is going to dictate wherever it's actually placed. The ones over on the green side is going to be your suction line ball valves. The ones on the blue line are going to be your liquid line ball valves. You can have ball valves all over a rack. So, I mean, really, wherever it is, I mean, on whatever line that it's actually connected to, that's what you'll refer it to. That one is a liquid line ball valve. That one's a discharge line ball valve.
Yeah, and the main thing there is that don't burn them up to begin with, so that way they actually do close when you need them to close. I don't know much, but I know that much because I've had enough of these suckers where you go to try to isolate and they don't isolate. And
either that or they start blowing refrigerant out of the packing.
Yeah, exactly.
Okay, let me take this one. On this solenoid, we have there's sometimes you can have biflow solenoid valves. So in the instance of that top solenoid, you technically wouldn't need that check valve if that was a biflow solenoid, where basically you could have flow in either direction. But these are all single way, one way solenoid valves. That are in this pictorial.
So depending on the system, you may have a liquid line solenoid valve, you may not. So it just depends on the customer setup. Like Brett was saying, we have these liquid line solenoid valves that we're going to have on here. Depending on the customer, some customers don't have liquid line solenoid valves at all. And if they're there for emergency shutdown and defrost. They're not actually controlling temperature with them usually. We have, after you leave that liquid line solenoid valve, we are going to come into our expansion valve. So we have a TXV. We're either going to have a TXV, a standard TXV, or a balance port TXV, meaning it's able to, a balance port TXV is able to handle greater swings in pressure and conditions. So like the tonnage of the evaporator can change a little bit more. It can handle that. So it has a greater control over that evaporator than a standard TXV. We're starting to see a lot more electronic expansion valves now. So as they become cheaper and controls become better, we're integrating a lot of new stuff as electronic expansion valves. So we have steppers. So we are able to control superheat to the minutest bit, and then we're also using what they call pulse valves now, which are basically a orificed liquid line solenoid that pulses on and off to feed refrigerant into the evaporator and control superheat that way. Those are going to be the three main metering devices. We don't use any cap tubes or fixed orifices or anything like that anymore. It is all going to be expansion valves, thermal expansion valves, EEVs, and pulse valves is what you're going to start seeing. And all of those are going to feed out into a distributor. Now, this distributor is just like you would have in an air conditioning system. It is distributing refrigerant to multiple different passes in the evaporator coil. Now, the things that are a little bit different about our distributors are systems that have hot gas defrost or cool gas defrost for defrost. We have a built-in T into these things. So it's not a T, but it's a auxiliary side connector. So what it is doing is it is taking the orifice that is inside of the distributor that creates the vortex and makes it feed evenly. It's taking that and moving it forward towards the expansion valve. So we do this because that orifice is very tiny. So we need to be able to move quite a good volume of liquid refrigerant back through that coil during defrost. That hot gas is going to go through and condense into a liquid, and it's going to come back through those distributor tubes, and then it goes into this ASC, and it's going to take a turn and go around the expansion valve through a check valve and then back into the liquid line. If that ASC wasn't there and it was just a T, what ends up happening is inside the distributor of a normal distributor is the orifice. So what ends up happening is it hits that orifice and instantly slows down, and you're never going to flow the proper amount of refrigerant through that T in order to properly defrost that coil. So that's where this auxiliary side connector comes in, and it allows you to move that orifice forward towards the expansion valve, and allows that refrigerant to bypass that orifice and go around the expansion valve through a check valve back into the liquid line. So that's where ours changes a little bit versus a normal distributor orifice and distributor. Then we go through our evaporator coil. So we go through our evaporator coil. It's no different than a normal evaporator coil, except for fin spacing. So we have a lot tighter fin spacing because we're trying to maintain these. Actually, it's a lot. It'd be less probably.
Yeah, greater distance between the fins. Yeah, wider space.
Yeah, so low temperature, we're having a wider fin spacing, and medium temperature, depending on it is. I mean, some of the fin spacing is probably pretty close to a normal evaporator coil you would see in a house now. I mean, these cases have become so efficient that the fin spacing is like super tight on them because they're trying to maintain that temperature difference from refrigerant temperature to air.
Well, don't forget to mention the most important part of the TXV is the strainer in front of the TXV. These supermarket systems can be extremely filthy. Whether it be debris from a compressor, debris from new systems being brazed in. This is the filters that are put in here just to ensure it's a small mesh screen that goes on the inlet of the expansion valve. Not every single expansion valve has it, as you guys know, in air conditioning, but in refrigeration, it's very just smiled upon whenever you have an expansion valve that does have a strainer in there to ensure that you can clean it, so the expansion valve itself does not become gummed up with debris.
Yeah, it's pretty rare to have a bad expansion valve. Most of the time in supermarkets, most of your time is spent cleaning stuff, just like basic maintenance. I mean, you spend a lot of time cleaning, whether it's cleaning evaporators, cleaning expansion valve screens, cleaning the pins on the expansion valves. You pull the expansion valve apart, you clean the pins, clean the orifice. They gum up. I mean, there's a lot of oil in the system, and a lot could go wrong real quick with the oil. And a lot of issues, stem from that. So a lot of screens will plug up. I mean, it just depends. The more maintenance you do on a system like this, the less problems you have. But I mean, problems always occur, and I mean that's why it's always so busy.
Yeah, for sure. Cleaning screens is like one of the, or swapping screens is like one of the most normal, usual things that you have to do in market refrigeration. It seems. Yeah,
it's very satisfying watching all that frost melt away from the valve as you start it back up. So now we come out of the evaporator. Now this is where our entire temperature control strategy comes in here on a supermarket. So on a supermarket, we're generally not controlling temperature by cycling a solenoid on and off. That is very poor control. There are certain applications where it gets used. It's on some budget stuff, but what we are doing is we are manipulating the evaporator pressure and saturated temperature. So what we do is we have this device called an EPR, Evaporator Pressure Regulator. So we are backing up refrigerant pressure inside the evaporator and setting the temperature of the evaporator. So I could set this evaporator temperature to anything I want. I can make this evaporator a 20-degree saturated temperature, I could make it a 19-degree temperature. I could make it a 35-degree temperature. So I could vary this evaporator temperature, which is going to vary my case supply air temperature. So we are trying to maintain return air temperature in a walk-in or supply air temperature in an open air case or frozen food case. We're trying to maintain that supply air temperature. We do this by changing the evaporator temperature. So every case manufacturer or store is going to have a legend, and it's going to tell you what the evaporator temperatures need to run in order to maintain a certain discharge air temperature. So we're able to manipulate this system. So I could be running a minus 20 saturated suction temperature on my compressors, and I could be running a plus 25 degree evaporator for some meat cases on that same header. By using that evaporator pressure regulator, I'm able to change that pressure and manipulate it and change the actual temperature of the case with this device.
So long as you're going up from your suction header pressure, the valve can't make it go lower than that. That's a common misconception I've heard air conditioning guys have, is that they think it can control it either way, but it's just increasing the pressure and therefore the temperature from what the suction header is.
Yeah, we can only go higher than what the saturated suction is set for at the actual suction header of the compressors that it's connected to. If we refer to air conditioning, right, we usually maintain a 38 to 40 degree saturated suction, right?
Yep.
And then usually the discharge air is anywhere from 52 to 55, right? So usually that would give you approximately about a 15 degree TD that's what we refer to in refrigeration. It's basically the difference between your saturated suction and your discharge air. And that's what we're accomplishing here. If we're trying to maintain 35 degrees, we would set the evaporator. If it had a 10 degree TD, we'd set it for 25 degrees. Exactly the same premise that you do in HVAC, just with lower temperatures.
Yeah, and that's another interesting thing, because in HVAC, we'll talk about TD. So we'll talk about design temperature difference, DTD or TD, and we refer to that as the difference between the entering air temperature and the suction saturation. And so we would say a common DTD would be 35, but in refrigeration, they refer to it as the difference of the supplier, the air returning to the box, versus the saturated suction. It's important that you get that distinction between the two segments. Otherwise you'll be like, what, 15, 35, what is it?
Yeah. And I mean, some of ours are, you see design temperature splits as low as, like, I was doing some cases this morning, they were 4 degrees. So we're maintaining 4 degrees from our evaporator temp. So I had a plus 27 degree evaporator, and I'm 4 degrees above that.
So 31 degree discharge air temp. And that's what makes all these cases more efficient now, right? They, years ago, it's the fin spacing is really what does it. The meat cases, they used to be about maybe 1.5 inches away from each other from fin to fin. And then they got a little bit smaller. And then, where the TD was originally, let's just say 15, the fin spacing then got less. And they're like, oh, we can get 10 degree TD out of it, so we can raise our saturated suction. And they're like, well, let's put a lot more fins in there and make it a lot more efficient. And then we can get it all the way down to 3-4 degree TD, which means we can raise our saturated suction a whole bunch more and actually save energy, right? Because then we're reducing, reducing the compression ratio, which means we're saving energy.
Yeah, absolutely. And then out of here, you just go right back into your suction header, and we're back to our compressors and all over again. A lot of people who are listening to this are probably like, man, like they missed like a lot of stuff. There's so many questions that I have. It's like, yeah, that's the reason why they have an entire podcast about all of it and not just a single episode. So this is like a lifelong pursuit, not something that you can cover, and all the different exceptions and types of system infrastructures, let alone things like CO2, and all this gets really, really complicated. I'm going to kind of turn it over to you, Brett, to kind of, wrap us up here and tell people how they can find your podcast, how they can interact with everything you're doing. You're going to be at AHR, any stuff you want to announce about what you got going on and how people can connect with everything you're doing.
Absolutely. So I'll be at AHR in Vegas. I'll be at the Sporland tent for the first 2 days from 12:30 to 5. You guys can come see me. Sporland's doing a giveaway. I'll be doing a giveaway as well with some Advanced Refrigeration podcast merch. We will both be at your symposium down in Claremont.
Yes,
coming up. So we will both be there. Tickets are already booked. They can find us at advancedrefrigerationpodcast.com. We have a site where we have all our merch, as well as we're on almost every single major platform, Apple Podcasts, Spotify, Google. You just look it up and you'll find it everywhere. And we also have started doing heavy controls videos on our YouTube channel as well.
Yeah, people will always ask, how do I find the podcast? Where do I find the podcast? Literally, easiest thing in the world. Go to any podcast app that you like. It doesn't matter. Pick one and type Advanced Refrigeration in the search bar and it'll come up, easy. And then also, they didn't ask this, but I'll just say it. Leave them a review. Once you listen to the podcast and you hear it and you like it, which you will, leave a nice review, leave a 5-star review, especially on Apple Podcasts, because that really helps the podcast rank. It helps people feel comfortable listening to the podcast. And so do that, subscribe. Again, this stuff is being given away for free for the benefit of the industry. The best thing you can do is just support them in that way. Tell your friends, that kind of thing. It's good. It's good work they're doing. And I'm excited that you guys took the time to do this. And I'm excited for what the future holds with you. You guys are doing great things.
Thanks so much for having us on, man.
Yeah, it's a pleasure. And we'll do it again sometime.
Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to hvacrschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.